Welcome back to The Explainer. Today, we're tackling a literal power struggle. We're diving into a massive shift in technology, looking at how researchers are fundamentally redesigning computer chips to work like the human brain. And in the process, they're trying to solve AI's looming massive energy crisis. Look, we live in an era where artificial intelligence can instantly generate art, write complex code, and hold highly nuanced conversations. But that incredible capability comes with a hidden, rapidly growing cost. So today, we're exploring a system inspired by the very neurons inside our own heads. To kick things off, just think about the staggering amount of electricity required for a massive model like GPT-4 to, say, write a simple poem. Now compare that to the tiny fraction of energy your own biological brain uses to do the exact same thing. Fun fact, your brain runs on about 20 watts. That is literally less than a dim light bulb. Meanwhile, modern AI operates by flooding microchips with massive quantities of binary signals, just endless zeros and ones, gobbling up electricity. Seriously, if your brain operated with the same brute force, energy-dense approach as a modern AI server farm, it would quite literally overheat. And this urgent energy crisis is exactly why scientists are going all in on neuromorphic computing. Now, we're not just talking about writing slightly more optimized code here, we're talking about tearing down hardware to the studs and redesigning it from the ground up to mimic biological nervous systems. That means integrating memory and computation together. And instead of using a rigid, continuously ticking clock to process data, it relies on asynchronous, event-driven spikes. Essentially, it only fires when it absolutely has to. It really comes down to a fundamental paradigm shift. See, traditional von Neumann computer architectures, the ones we've relied on for decades, keep memory and computation totally separate. In a standard computer, data is constantly being shuttled back and forth between the memory module and the processor. And that constant movement creates a massive bottleneck, wasting a ton of energy. But in the neuromorphic paradigm, the memory is distributed directly within the synapses themselves. Each neuron acts as an autonomous unit, processing information locally. It cuts down on power consumption dramatically. Stanford's Dr. Bohin actually hits the nail right on the head with this. He says that today's neural networks are about as similar to a brain as an airplane is to a bird. He's a real pioneer in this field. Growing up in Ghana, he used to take apart electronics just to learn how they worked. And he later realized that modern computers really just rely on sheer circuitry volume rather than elegant design. He points out that if the 86 billion neurons in our brains were constantly firing binary signals at each other the way AI nodes do, our heads would roast. So we clearly need a new way forward. So let's look at the actual hardware. Section 1, hardware, the silicon brain, Intel's Loihi 2, and the power of nanodendrites. Tech giants and university research labs are pouring serious time and money into turning these wild, brain-inspired concepts into physical reality. And the results are genuinely mind-bending. Take Intel's Loihi 2, for example. This is an advanced neuromorphic research chip that somehow packs 1 million digital neurons into a single processor. And this isn't just a conceptual drawing. It is a physical piece of silicon. It utilizes 128 fully asynchronous neural cores that are entirely programmable. Instead of standard zeros and ones, all the communication between these cores takes the form of spike messages. It moves us a massive step closer to how human biology actually processes data. And the sheer efficiency of this thing is honestly incredible. The Loihi 2 handles up to 120 million synapses on roughly, get this, 1 single watt of power. It pulls this off by completely ditching a constant central clock in favor of that asynchronous, event-driven networking we mentioned earlier. To put that into perspective, a standard AI graphics processing unit can easily pull hundreds of watts of power. By using biological principles, this chip operates at an energy cost so low it could run off a tiny battery. Plus, because the neuron models are fully programmable, researchers can adapt the hardware to emulate really complex, nonlinear biological behaviors. So how do we push that efficiency even further? Well, it's all about what researchers call the dendrocentric shift. By utilizing nanoscale components like nanodendrites, we can shift away from processing a flood of constant binary data. Instead, we rely on sparse, highly meaningful sequences of spikes. Stanford researchers proposed this approach where, instead of keeping half the computing nodes on at all times, the system waits for specific temporal sequences of spikes, almost like deciphering Morse code. A neuron only fires if its artificial dendrite detects exactly the right sequence. This sparsity could potentially cut the signaling required for a massive AI model like GPT by an astonishing 400-fold. No way, right? But it's true. Which brings us to Section 2, mapping artificial neuron behavior, deciphering the spiking neural network. Now, you might be wondering, How on earth do scientists actually measure and program the behavior of these microscopic, unpredictable artificial neurons? Well, enter the research of Riccardo Pagnari and something called the Neuronal Phase Map, or NePhaM for short. It's basically a visual tool that allows us to map exactly how specific parameters change an artificial neuron's behavior. Because complex neuron models have multiple dimensions of parameters, plotting them out manually is pretty much impossible. The NePhaM pipeline solves this by simulating the neuron across a range of inputs and turning the resulting behaviors into a simplified, two-dimensional grid of pixels. It literally gives engineers a map to navigate the chaotic potential of these spiking networks. And these simulations build up into these incredibly detailed, colorful matrices. For instance, if we look at the behavioral maps for the Isaacevich model, which is a highly realistic yet mathematically efficient model of a neuron, we can see distinct zones. Certain areas might show steady, continuous spiking, while other areas signify totally undefined, unpredictable behavior. By using these visual maps, hardware designers know exactly which parameters to lock in so the chip performs reliably without falling into that chaotic, unpredictable zone. Calibrating these precise behaviors is absolutely critical. It's the key to successfully encoding real-world sensory data into a language that these spiking neural networks can process efficiently. Think about an artificial eye trying to talk to a neuromorphic chip. We have to translate that visual data into spikes. For some data, we need tonic spiking, a steady, continuous rhythm, kind of like a heartbeat. Or for a sudden change, we might need phasic spiking, just one sharp, isolated alert, like a smoke alarm going off. By meticulously mapping these characteristics, we are essentially creating the very interface between the physical world and the silicon brain. Moving on to Section 3, the future of Edge AI, intelligence everywhere at a fraction of the power. So when we combine these perfectly tuned silicon neurons with extreme energy efficiency, where does that actually leave us? Well, as we start moving away from cloud-dependent AI that relies on massive remote server farms, the neuromorphic paradigm opens the door to embedding high-level intelligence directly into the devices all around us. Because this hardware can handle intelligent sensing tasks like complex audio processing or optical flow up to 90 times more efficiently than standard deep neural networks, we're looking at a total revolution in on-device edge AI. We are already seeing research where chips like the Loihi 2 process optical flow from cameras or manage radio resources on satellites out in space. This means your everyday devices can process incredibly complex data locally, in real time, without suffering the latency of sending it back to the cloud, and crucially, without burning through their energy reserves. I'll leave you with this final thought for today's explainer. I want you to imagine a future where the devices right there on your wrist or scattered throughout your home hold immense, supercomputer-level AI power, but they run on a standard battery without ever dying. What monumentally amazing things could we build with that? By studying the elegance of biological nervous systems, we aren't just saving electricity. We are entirely redefining the boundaries of what computers can do in our daily lives. Thanks for joining me, and keep questioning how the future is built.